Welcome back. So we're continuing our discussion of SVD, and SVD, as we saw last time, can apply to matrices which are not square. And in the context of our y equals ax problem, if we have a non-square matrix, we may have a system that's overdetermined or underdetermined. And this is especially meaningful if we have noise in our observation, because that system may not be solvable. We may not be able to find x. However, so we're going to talk about ways of finding that, but before we get there, just an aside, something I maybe should have talked about last time. That is something we'll find useful going forward. We have our singular value decomposition of A, given like so. This could be written as a bunch of column vectors, TUR times our sigmas, our singular values, times our row vectors, V1 transpose, V2 transpose, and so on and so forth, to VR transpose. So if we go and multiply that out, we're going to get sigma, actually we're going to get a sum, r equals 1 to capital R, of sigma r times the vector UR, the vector VR transpose. So we have a decomposition basically works of A in terms of a sum of rank 1 matrices. So this is an outer product here. And this is very similar to the spectral decomposition that we talked about with respect to our square matrices. Okay, so let's get back to our problem, which is we are trying to solve y is equal to ax. And it should be no surprise, since this is what we're talking about right now, we're going to want to use SVD. And just as a reminder, y and x can have different dimensions. A then be an m by n matrix. Okay, so if we have an overdetermined system or an underdetermined system, let's decide what a good solution to this would be. So, given some set of observations y, we want to find x in a reasonable way. And we'll define that as 1, when a unique solution exists, we're going to want to use it. Next, when no solution exists, we want to return something reasonable. And finally, when there are an infinite number of solutions, we want to choose the best one. I understand that none of this is very precise. So we need to come and define what's reasonable and what's best. But that'll be the topic of today's lecture. So first, let's define a residual. And I'm going to say that R, sorry, we're reusing our variable R in many ways. R is equal to y minus ax. And so we can then talk about coming up with something that's a close solution or a reasonable solution. So in the least squares sense. So we'll have a least squares framework, and we do some optimization to find our best solution. We want to find the x in Rn such that y minus ax norm squared is minimized. Okay, let's see how this works. So in this case, maybe no solution exists. We're going to find something reasonable. If we have an infinite number of solutions, and then we can probably come up with the minimum is R. I mean, the minimum value of that of our residual would be 0. And so we're going to have to come up with a different representation for best, but this should at least address problem 2. Above. Okay, here's our solution. We're going to let x equal v alpha plus v naught alpha naught. And redraw these just to make it clear. X is a vector, alpha is a vector, alpha naught is a vector, and our v and v naught are matrices. So we can write this in another form as a matrix made up of, by smashing those two together, we'll have our vector alpha and our vector alpha naught right there. So that's our expression for x. Okay, a few notes about v. So v, as we know, is n by r, and this is the same v that we had from our SVD, where we had a is equal to u sigma, and then I got to remove a bit here. A is equal to u sigma v transpose. That's the v we're talking about. So v naught is a new thing. V naught is going to be n by n minus r. The columns of v naught are orthonormal, and they are orthogonal to the columns of v. Okay, so in practice, what does this mean? Well, we have some n-dimensional vectors. Each of our vectors in V are columns, have n dimensions, but we only have r vectors. In V, those vectors are orthonormal, so we're spanning a subspace of dimension r, where r is less than n. That's nice. X will have some, perhaps, component within that subspace, but it's not constrained to that subspace. X is n-dimensional. So what we're doing is we're saying, okay, let's just fill out and create an entire orthonormal basis for Rn. And so that's what this is. This is our subspace from our SVD. In addition, this is now V0 is spans the subspace not spanned by V. So this is now a orthonormal basis for Rn. So a few properties that come from that. We have V transpose V is equal to I. We already knew that. And likewise, we're going to have V0 transpose V0 is equal to the identity matrix. And because these are orthogonal to each other, V transpose V0 is equal to 0. So our last property, which comes from the fact that we have an orthonormal basis, is that if we took our orthonormal basis, meaning the columns from the matrix V0, we're going to get n by n identity matrix. Okay, so setting this up, and since we have an orthonormal basis, we will have that alpha is equal to V transpose X, and alpha naught is equal to V naught transpose X. Now this is just a property, once again, of orthonormal bases, and you might recall that I warned earlier on in the semester when we switched from just some basis where we had to use a Gramian to orthonormal. This is the result. So if this wasn't orthonormal, we'd have to use a Gramian, but we don't, because we have an orthonormal basis. So you could note that now we have X is equal to V alpha plus V naught alpha. That would be V transpose X plus V naught transpose X, which is equal to V transpose plus V naught transpose times X which is just equal to X. There we go. Okay, now we need to define some new quantities here. This next one, we have Y is equal to U beta, I'm going to make beta a vector, make it bold, plus U naught beta naught. And this is going to be defined in essentially the same way. So we'll have U transpose U is equal to I, and U naught transpose U naught is equal to I, and U transpose U naught would be equal to 0, and U naught, that matrix transpose times U naught is going to be the M by M identity matrix. And as before, we have beta is equal to U transpose times our Y vector, and beta naught is equal to U naught transpose times our Y vector. Okay, now that we've defined all these quantities, I think we have the framework that we need to finish our little least squares analysis. So as you recall, we had R is equal to Y minus AX, and now we can express that as U beta plus U naught beta naught minus A, which is U sigma V transpose, times X, which is V alpha plus V naught alpha naught. Well, of course, V naught times V transpose times V naught goes away, is equal to 0. So now we get U beta plus U naught beta naught minus U sigma. Now V transpose times V is just the identity matrix, so we're going to have our vector alpha there. Okay, well, we can do just a little bit more with this. Let's do U. Actually, let's do U naught times beta naught plus U times beta minus sigma alpha. So that's our R. And we want to choose our alpha that minimizes the norm squared of R. That was the whole point, right? We wanted to find the minimum X of R squared. So that means, well, how do we do that? Well, it turns out that the entire contribution to this whole problem of X was just due to alpha. Alpha naught had no impact on the residual. It gets killed, if you will, by V transpose, or by the matrix A. So now we just need to find alpha to minimize norm squared of R. So, well, we're getting a little closer, I think, to a good solution. Let's see what we could do. So, norm squared of R is going to be our little inner product face. So that goes into both of those terms. And this can be expressed as U naught beta naught, U naught beta naught kind of following the FOIL method here. First, outer minus 2 times u naught beta naught with u beta minus sigma alpha plus, last would be, I think that's a plus there, u beta minus sigma alpha with u beta minus sigma alpha. So, well, when we evaluate this second term, we will have a u naught transpose, or u transpose times u naught, because we would transpose this second expression here and multiply it by that. So right in the middle of it all, we're going to evaluate to 0. So that goes away. And all we're left with then are these two terms. Well, that was a nice little exercise. We can go ahead and put this back into another form. U naught beta naught squared plus u times beta minus sigma alpha squared. Okay, so a couple things to note. This is not a function of alpha. So if we're trying to minimize r squared as a function of x, which we found was equivalent to minimizing r squared as a function of alpha, then that's, the first term isn't going to do us any good. So let's focus our attention on the second term, and this will be minimized when alpha is equal to inverse of sigma times beta. And that would give us beta minus beta times beta, or beta minus sigma times sigma inverse times beta would be beta minus beta on the inside, and then we get u times 0 and the whole thing goes away. So that's great. Now we know what alpha is. We can write down our solution. So the x, which minimizes the norm of r squared, is simply we'll call it x hat here to show that it's a minimization, not a pure solution. V alpha hat is equal to V norm, I'm sorry, V times sigma inverse times beta. Well, where did we get beta from? That was sigma inverse U transpose Y. So I suppose we should make a big deal of this. There we go. So we can just kind of see how this plays out. Let's stick that into the solution. So in this case, remember we have A is equal to U sigma V transpose. So AX is equal to U sigma V transpose V sigma inverse U transpose Y. Well, that goes away. It becomes an R by R identity. And likewise, those, as we work out, cancel. Another R by R identity. So this whole thing then is just equal to U transpose Y.